Hi viewers, you're welcome to my channel. Today's topic, let's look at factors that affect the solubility of sparingly soluble salt. So number one factor is common ion effect. If we dissolve a sparingly soluble salt such as barium sulfate or barium sulfate 6, you have so many of them, silver chloride, magnesium sulfate, and so on and so forth. The solubility expression for this. So what happens when we introduce barium chloride to this saturated solution? So this is the solubility equilibrium for this. Alright, so you can see the ions present in barium chloride, barium ion. This chloride ion is not here. So it means that if you introduce barium chloride into a saturated solution of barium sulfate, what happens? You are introducing more barium ion. It means you are increasing concentration of barium ion. So, according to the Chern principle, if you increase the concentration of the product, what happens? Every position is going to shift to the left to favor the formation of solid barium sulfate. So it means that the solubility of barium sulfate will decrease in the presence of its ion. That's what we call common ion effect. Look at silver chloride. If I introduce sodium chloride into a solution of second solution of silver chloride, the solubility of silver chloride will decrease. It's going to reduce. So there are so many examples. I have magnesium sulfate. If I introduce potassium sulfate into this second solution of magnesium sulfate, the solubility of magnesium sulfate is going to decrease because of common ion effect. So the common ion effect is a decrease in the solubility of a sparingly soluble salt due to the presence in solution of a common ion. Let's look at number 2 factor that affects the solubility of a static soluble salt. Number 2 is a salt effect, or what we call uncommon ion effect. So it is known that the solubility of a sparingly soluble salt increases in the presence of ionic compound which does not have common ion with the original compound. So look at this, for example, magnesium triazole carbonate 4, magnesium carbonate. If I introduce potassium chloride into this solution, such a solution of this, let's say 0.1 molar concentration of potassium chloride into the saturated solution, what will happen to the solubility of this? It's going to increase even by 5%. So uncommon ion effect, solubility increases. So we're going to be solving exercises on this. So to get the molar solubility of barium sulfate, Ka2 of barium sulfate is 1.1 times 10 to the power minus 10 in the presence of 0.02 molar barium chloride at 25 degrees Celsius. 0.02 mole per dm cube of barium chloride. So this concentration here is 1 mole, so the same thing, 0.02. This one is 2 mole, so 2 times 0.02. This one is 0.004 for chloride ion. Alright, equilibrium expression for barium sulfate. So this is barium sulfate. Alright, so we don't actually know the concentration, what it means. So let it be S. If it's S, barium ion will be S plus this additional one, barium ion from barium chloride. So it will be plus 0.002. So this one, sulfate ion is also 1 mole. So put it S. So let's write KSP for this, KSP. So KSP for barium sulfate. So have barium ion times sulfate ion So the SU value is 1.1 times 10 raised to the power minus 10. So I'm going to substitute this value into the concentration of barium ion and sulfate ion. So we have barium ion is X plus 0.002 times S equals to 1.1 times 10 raised to the power minus 10. So when you factorize this, so you have this. So this is A, this is B, and this is C. So using a quadratic equation to solve this, so substitute your values into it. This is B. So this is your B square, 4 times 1.1 times 10 raised to the power minus 10. So when you square this value and subtract from what you have here, you'll be having 4.004. 4 times 10 raised to the power minus 6. So the square root of this will have 0.020. You have to take it up to this so that we will have this 0.02, which is nothing as this. So 0.0020011. So when you divide it by 2, x is minus 2 times 10 raised to the power minus 3, or 5.5 times 10 raised to the power minus 7. Calculate the solubility of barium hydroxide in the presence of 0.05 concentration of barium chloride. So this is the equilibrium equation for barium chloride. So barium chloride, the ions present are barium ion and chloride ion. So since the concentration of barium chloride is 0.05, you have 1 mole for barium ion, that's 0.05. 2 moles of chloride ion, that's 2 times 0.05, that's 0.1 mole. Okay, look at this. We're going to write a solubility equilibrium equation for barium hydroxide. For barium hydroxide, the ions present are barium ion and hydroxide ions. So we are looking for the molar solubility of barium hydroxide. You say let it be X. Of course, barium, this one is S plus the common ion effect. The ion, barium ion, the one from barium chloride, common ion effect, barium ion, the concentration is 0.05. So we're going to add it here, plus. So 0.005. We don't have anything to do with chloride ion. There's no common ion effect. This is hydroxide ion. So this one is 2 moles, so it will be 2x. So next step, we're going to write KSP equation, which is barium ion times hydroxide ion raised to the power 2. So what's the value for KSP for sodium hydroxide? 5.1 times 10 raised to the power minus 8. So let's substitute this value into this. So x plus 0.05 times 2x squared equals 5.1 times 10 raised to the power minus 8. Alright, so we're going to be using the other method, not quadratic equation method. So this x, value of x is very small to compare to 0.05. So what means that x plus 0.05 moles equals to 0.05. So 0.05. So square, 2 squared is 4. 4 s squared starts 4s squared. So what we have here. So next thing, 0.05 times 4. So we're having 0.2, that's 0.2 s squared equals to 5.1 times 10 raised to the power minus 5. X squared will be 5.1 times 10 raised to the power minus 8 divided by 2. So the value will be 2.55. Square root of this value, the square root of 2.55 times 10 raised to the power minus 7. 5.05 times 10 raised to the power minus 4. So therefore, since the concentration of the barium hydroxide is S, the molar solubility of barium hydroxide is 5.05 times 10 raised to the power minus 4 mole. If you also want to use the other method, look at this from this place now. So this S times 2S squared will be 4 S raised to the power 3 plus 0.05 times 4S squared. You will have 0.2 x squared. So equals to this value, the KSP 5.1. So you consider this value to be too small. So we'll be using this 4s raised to the power 3. You'll be working with only 0.2 s squared is equals to 5.1. So you get the same answer. Determine the solubility of lead 2 chloride in 0.1 mole calcium chloride. So the KSP for PbCl2 is 1.7 times 10 raised to the power minus 5. So we'll start by writing equation for calcium chloride. So the ions present, calcium ion plus 2 moles of chloride ion. So if you have 0.1 molar calcium chloride, here is 0.1, and here will be what? 2 times 0.1, that's 0.2. So let's look at solubility equilibrium equation for lead 2 chloride. Alright, so we are looking for, let it be S. So this one also be X mole. So the common ion effect is the chloride ion from calcium chloride. So it will be 2x plus 2s because of this 2 moles here, plus the concentration of chloride ion from calcium chloride plus 0.2. So KSP times chloride ion raised to the power 2. So the value for KSP is 1.7 times 10 raised to the power minus 5. So I'm going to substitute this concentration into this. So we have X times 2x plus 0.2 squared. 1.7 times 10 raised to the power minus 5. Alright, so as usual, we're going to consider this S to be too small to compare to 0.2. So what I have here is I have the 2s plus 0.2 squared equals to 0.2 squared. That's what it means. So what I have here will be x times 0.2 squared. I won't consider this. So 0.2 squared is 0.04 equals to 1.7 times 10 raised to the power minus 5. 0.04x is equals to 1.7 times 10 raised to the power minus 5. X is equals to 1.7 times 10 raised to the power minus 5 divided by 0.04. So that's value for x. It's from this point. If you want to expand this, for example, if you expand this, x 2 squared, 2s squared is 4s squared plus 0.2 squared is 0.04. So if you factorize this, you have 4 s to the power 3 plus 0.04 x is equals to 1.7 times 10 raised to the power minus 5. So this value, you consider this one to be what? To be very small. Too small, this value. You only work with this, you still get the same answer. Calculate the molar solubility of magnesium carbonate in the presence of 0.1 sodium tetracarbonate 4. So KSP for magnesium tetracarbonate 4 is 3.5 times 10 raised to the power minus 8. So start by writing the equation for sodium tetracarbonate 4. So how many moles? 0.1 molar concentration. So this one will be 2 times 0.1, that's 0.2. And this is 0.1. So that's all of the tetracarbonate 4 is X plus the ion coming from sodium tetrahydrocarbonate 4, which is 0.1. So KSP. So magnesium ion times tetrahydrocarbonate 4 ion equals to 3.5 times 10 raised to the power minus 8. So I'm going to substitute this value, the conversion into this. So we have X times X plus 0.1 equals to 3.5 times 10 raised to the power minus 8. Alright, so S times X, you have X squared plus 0.1. Okay, as usual, this S, we assume that X is very small to compare to what? 0.1. So what we're working with, X times 0.1. So X times 0.1 is equals to 3.5 times 10 raised to the power minus 8. So X will be 3.5 times 10 raised to the power minus 8 divided by 0.1. Let me expand this. Let me expand from here and say S squared. S times 0.1 plus 0.1x is equals to 3.5 times 10 raised to the power minus 8. So this value is small. So compared to 0.1. So when you're working with 0.1s, you will still get the same value. If you use quadratic equation, you will still get what? The same answer. Okay, this particular question, I would like you to use quadratic method to solve this. Whatever you get as your answer, post it in the comment section. Alright, so we'll come to the end of the lesson. The next video I'll be uploading will be on reaction quotient and solubility constant. Thank you for watching and do have a great day. Bye.